Welcome to Brain Vision.
Okay, so question 21. Robbie Knievel ride. On May the 20th, 1999, Robbie Knievel easily cleared a narrow part of the Grand Canyon during a world record-setting long-distance motorcycle jump, 69.5 meters. He left the jump ramp at a 10-degree angle above the horizontal. How fast was he traveling when he left the ramp? Indicate any assumptions you made. Okay, so, well, there's an awful lot going on here. There is some gap that has to be traversed. And at the same time, we are leaving with a velocity, an initial velocity. We'll just mark that as u, the letter u, with 10 degrees to the horizontal as our launch velocity. Okay, and so first of all, we've definitely got two directions in which everything acts, the horizontal and the vertical directions, and we're literally saying that y is the vertical and x is the horizontal. And so it's worth doing what I usually do, which is to note a few interesting characteristics across everything. And call these Suvat equations, if you're familiar with them or if you're not. Basically, s is the distance in which you go, u is your initial velocity in that direction, v is your final velocity in that direction, a is your acceleration, and t is time. And these are all interlinked. So we know that we travel at 69.5 meters if we're at Robbie Knievel. And we've got some velocity that we don't know, u0. Let's call it u0 in the x direction, but of course it's not just in the x direction, it's u0 cosine of 10 degrees in the x direction. And of course, our final velocity is likewise equal to u0 cosine of 10 degrees in the x direction because we are ignoring air resistance. So there is no change in acceleration. And time? Well, we'll just call that time. We're just trying to get an establishment of what we know. So to clear our gap, we're assuming no change in height. Ideally, we should not go negative. And in the limit of the equation, we should not go below 0. So our height starts at 0, it ends at 0, and it does not go below 0. Our initial velocity, therefore, is equal to u0 sine of 10 degrees. And here's where we get a little clever. Because our final velocity in the y direction, at the very limit, well, our path is going to be a symmetric one. And so, if we were travelling at u0 sine 10 upwards, when we took off, we should be travelling at negative u0 sine 10 degrees when we land. We'll see if this helps us later. But this is a symmetry argument. Our acceleration is obviously negative because we've defined upwards as positive, but it's 9.8. It's the gravitational constant. And of course, t is just equal to t. Right, so let's jot up some equations in the y direction. Well, we know that our final velocity is going to be equal to our initial velocity plus our acceleration multiplied by time. And therefore, negative u0 sine of 10 degrees is equal to u0 sine of 10 degrees. So that's our final velocity and our initial velocity both in there, minus gt. And rearranging around a little bit, we get, of course, that gt is equal to 2 multiplied by u0 multiplied by the sine of 10 degrees. And let's rearrange for t. Our time, therefore, is equal to 2 multiplied by u0 multiplied by the sine of 10 degrees divided by the gravitational constant. Right, what's going on in the x direction before we start getting clever? Well, there's no acceleration in the x direction, so whatever distance that we traverse, whatever s we have, is got to be equal to u0, this is our velocity, our initial velocity, cosine of 10, which takes us into the horizontal velocity multiplied by the time. And we can make a similar argument. We know that our initial velocity in the x direction is 69.5, and everything else we don't know. So 69.5 divided by u0 cosine 10 is going to be equal to the time that it takes to do this jump. And so let's start doing something mathematical. So we say therefore, because we have an equation for t here, an equation for t here, so here and here, we can say that 2 u0 sine of 10 degrees divided by g is equal to 69.5 divided by u0 cosine of 10 degrees. And this is a very true statement. The only unknown we have here is u0. And so we rearrange. We multiply both sides by u0. We divide by 2 sine 10 and multiply by g on the right hand side, leaving us simply with u0. I'm sure you guys can do this. This is mathematically a little bit interesting, but not ultimately very hard. Leaves us with 69.5 under a square root. Sorry, we don't need a u0 squared here, of course. A u0 simply is equal to this multiplied by g, 69.5 multiplied by 9.8, divided by 2 sine of 10 cosine of 10. And we can see this potentially as a double angle formula, but we don't need to do that. Simply we have to substitute our values into a calculator to find that our u0, our initial velocity, which we were projected with, is equal to 44.6 meters per second. And of course, this is basically the question. What velocity did he use to clear this jump? How fast was he traveling when he left the ramp? And we need to indicate any assumptions we made when we answered the question. And there are probably two. One is the classic of no air resistance. And the second is, of course, that you take off and land at the same height. It's a couple of very small assumptions, the first of which is a lot larger. No air resistance does affect this entire equation a lot. Takeoff and land at the same height is very, very pedantic. But these are the equations you need. This is the key answer. This is the velocity that you need to take off with, 44.6 meters per second. So it was going quite fast. And this is the answer to question 61.